Yeah. So that's kind of our goal today is to practice this a couple times. But along the way, my plan is to kind of stop and address kind of what we're overall trying to do, um, and some of the kind of concepts that we're working on along the way. Uh, yeah. So let me try to pull up. There we go. Um, okay. So yeah. So please feel free to stop me along the way. Again, much of what we're doing here, it, the actual math is not the difficult part, especially if you felt comfortable, with the material in chapter 9, or what you had to do on the exam and whatnot. Much of what we're doing here is similar. Um, it's really about trying to keep track of everything and all the moving parts, and kind of our process with regard to that. That takes a little more um, time. So let's jump in here soon. I should mention, again, your exams take some time to comb through. So I'm in the middle of that process. When Sorry, my hair is out of control. When that's done, I'm not entirely sure, but I expect, you know, um, early next week to be wrapping up all of them. Um, as I mentioned, and I believe emailed out, the assignment for chapter 10 is not due until next Tuesday. Again, there's a lot in here, and I don't want you to rush after I assume you took a little time, a little break after the exam. So, but yeah, so there's a lot. So if you haven't started getting into it, I encourage you to do so soon, as we'll see. There's kind of a lot of moving parts here. Um, and all right, so I think it'll be helpful to just kind of have an example or two that we can talk about as we move through. Um, and as you notice, if you and so chapter 11, it'll be up this weekend. I'll have chapter 11 posted, the assignment, so that you can start digging into that too. If you're trying to maintain your current kind of flow, doing things, typically we've had them do Sunday night, and chapter 11 will be due that following Sunday night. So I'll make sure that is up before Monday. Yeah. So, right. So if you have started into the homework assignment, you'll see kind of a common problem that you'll approach is one of a production line, and that's because this is a pretty useful technique for verifying production systems. So you have an assembly line that is doing repeated tasks, whether by hand or machinery or whatnot. But occasionally you want to make sure that the process is running smoothly, right? Nothing's broken down along the way, or some machine isn't malfunctioning. And one way we can do that is to sample the product at the end, or at various points along the way, to verify that we're pretty confident that the process is running smoothly. Okay, and so you do see this actually in play in production facilities, or some variation of this. Okay, this concept works for kind of what we're showing in the assignment, and we'll walk through kind of a similar one here. So just to kind of give us a example to talk about, let's say that we start making, we come up with a new type of pretzels. Maybe you like maybe we have a new competitor for Dots pretzels. You come up with some equally addicting type of pretzel, and so you've expanded, and now you have this production facility where you're pumping out bag after bag of we probably need to brand it something other than dots. Dots and I don't know. I'm just stuck on the candy dots. So you have your pretzels, and you're making bags of pretzels, and you want to make sure that each bag has the right amount of pretzels in it, right? And so we'll probably measure that in grams. And so let's say we're packaging our bags and we're claiming that there are 290 grams in each bag. Now, we want to make sure that that is true, okay, or within reason to be true, okay? So a lot of what we do here is assuming that the null hypothesis is true, and really when we say that, we say it's not statistically different than what the null hypothesis is saying. So when we say, so we're going to set this up as the null hypothesis, the mean weight of our bags is 290 grams. And really what we're saying is that it's not statistically different than that. So it might be 289.5 or 292 at any given time, but we're saying it's basically 290. Now, why do we want to verify or kind of monitor that this is true? Probably for two reasons. Number one, if we start giving bags out with 297 grams, that's profit that we're losing, right? We're giving away free pretzels. And so we want to make sure that we're not overfilling the bags. And on the flip side, if we're claiming 290 and we start giving bags out that are 270, we're liable for some type of a probably consumer fraud issue. Okay, so we do have incentive to make sure that it's kind of within a reasonable window here. And so we claim 290, and so we're going to set up, in this case, that the null hypothesis that, yes, everything's running smoothly. Okay, so again, this is kind of a decision as to how we want to set up the null and the alternative. And oftentimes, if we're simply trying to verify our production process, we'll often say, all right, let's assume that things are true here, and see if there's any evidence to the contrary. Okay, much like in previous ones, we've said maybe there's an outlandish claim, or maybe it's a reasonable claim by a politician, if those exist. We say, a politician says, there's been an average of people work an average of 3 hours more per week under our administration or something, and we can go ahead and try to see if that's a reasonable statement. So we've set up the null hypothesis that we've got 290 grams in each bag, or an average of 290 grams. Then that means that our alternative is the mean is not 290. Okay, and again, because we're concerned about both directions, we do want to be clear about that when we set up our null and alternative. And that's going to factor in later on when we turn to actually testing this. Okay. So, and specifically, again, what I'm highlighting there is that what we've done here in the middle here, where we've set up, this is a two-direction concept here, right? We want it to be, it's not at least 290. We're not making the claim that we fill our bags with at least 290 grams. Okay, so next, right, in our step 2, we want to say, how much evidence do we want, will we need to reject the null hypothesis, right? Because what our process is going to be is we're going to take a sample, we're going to examine that sample and say, is this enough evidence? Does this show a sample mean that's far enough away from 290 that we think there might be an issue? This is a decision that will, this could go a few different ways, and some of it for this situation might be how big of a deal is it if we have errors in this, right? So eventually we'll talk about type 1 and type 2 errors, and we'll be wanting to make this decision: how much significance do we need with within that frame of reference of type 1 and type 2 error. Now, for your purposes, as you try to get through the assignments, oftentimes it's given to you, right? Just like we kind of gave you the confidence interval, because that's not really, those decisions need to be made, and it's up to us. But so let's pick one. Let's say we want alpha to be written correctly. We want an alpha of 0.10, or a 10% confidence interval. No, not confidence interval. I keep making that mistake. A 10% level of significance, right? Again, this is the flip side of the 90% confidence interval, at least mathematically. So here is a case where, moving to step 3, this might actually be a case where we know the sample standard deviation, the population standard deviation. I need more coffee. Okay, so in chapter 9, we talked a lot about how it's unlikely that we know the sample standard population standard deviation, and we often have to rely upon the t statistic in using the sample standard deviation. Now, we could do that here, but with something like a production process, it's probably reasonable to rely upon the population standard deviation. We would have enough kind of evidence throughout our production process that we might know the population standard deviation of bag weights. So let's start with that and say we do know. We don't know anything because my iPad is freezing. There we go. So let's say we know the population standard deviation is, say, 5 grams. Because of that, when we turn to thinking about what test statistic we want to use, we know we can use the z statistic. Okay, so in step 3, we're really, in our case in chapter 10, we're determining between basically the z and the t statistic. In chapter 11, we will broaden that to some more possibilities. Okay, so we're going to rely upon the z statistic. And what we will eventually do is calculate a z statistic. And again, so it'll be, we'll make this calculation and determine if we have found enough evidence to reject the null. Now, what are we really saying here? So again, when we set up the null hypothesis, we are assuming, we're going to go with the assumption that that's true. Okay, so we're working from the framework that, let's assume that the null is true. Even, again, I want to stress this, that even if it's an outlandish claim, so even if a politician says something almost assuredly wrong, we set up the null in that it's true. And then we work from there. Okay, so what does that mean kind of graphically? That means that we're working with the normal distribution centered around the mean that we are assuming is true. So for us, get out of the way a little bit. For us, that means that we are working with the normal distribution that is centered around, it's not very symmetrical there, centered around 290. Okay, now it's important to remember that when we go ahead to test this in step 5, when we take our sample, we're not finding the population mean, right? When we sample, we find a sample mean. So we're going to find an X bar, right? And we know, again, that this this distribution is going to be normally distributed because we're taking samples. So this is the normal distribution in which we're working, where the distribution is centered around 290, but we know that there's a range in which we might find a sample. Okay, so we might take a sample and find 270. We might take a sample and find 285, right? And so by now, hopefully, we kind of understand how that distribution looks. And so at the heart of this testing is that we are assuming that most of our samples are going to fall within a certain range based on this normal distribution. If we were to find something that is extreme enough, we would have at least enough evidence to say there might be something wrong with our assumption. It might not be true that the null hypothesis is true or that the mean is 290. So, and this is, I think, sometimes overlooked, that we are not saying that anytime we get something, a sample mean that is not 290, if we get some sample mean that's not exactly 290, that's not necessarily enough evidence to reject the null, right? Because we know that these sample means bounce around a little bit. So let's say, let's assume, just to put some numbers on this, that we're going to sample every hour. We're going to sample 15 bags of pretzels. Okay, that's how we're going to kind of monitor it. We probably do some type of a systematic random sampling, right? Every, 20th bag comes off the conveyor belt and we weigh it more precisely. That might be the process, but somehow we're approaching kind of a random sample. And so what we know from chapters 8 and 9 is that each of those 15 bag samples is not going to be exactly 290, even if the population mean is 290. And this is where it comes down to understanding that distribution of sample means. Right? Understanding this distribution is of sample means, and that they're not always going to fall at 290, and in fact almost never will be exactly 290. Right? We might find 287.623, and that's a pretty reasonable outcome if the mean is in fact 290. And that's really what we're after. Are these results reasonable if the null hypothesis is true? If we find something extreme enough, we would have reason to say this is not something that's likely to occur when the mean is 290. Okay, so so when we take a sample, and for instance, maybe we take a sample that says, what did I say, 287.5 or something, and we can crunch exactly if that's true enough. That's probably close enough that that's not enough evidence. Okay, we wouldn't be too concerned. Now, if we find something that's 282, maybe that's far enough away, maybe it's not. And so what we're going to do in step 4 is structure out exactly how far out we would need to find the values. Okay, so let me just clean this up a little bit. Again, we've decided to set a 10% level of significance. Remembering, of course, that this is two-tailed. So really what we're saying is we know the sample mean is going to jump around. If we find a sample mean that is in the bottom 5% or the top 5% of possible distribution, then we have evidence to suggest that the null could be rejected and that the mean might not be 290. Now, of course, as we'll turn to in a little bit, it might still be true that the mean is 290. We could be producing an error here. And that would be a type 1 error. But we have reason to at least reject the null, and we might want to look deeper into it. And really, that's probably what our process is, or our goal here is in this production kind of concept is let's what happens if we flag this, if we get a sample that's too extreme and we think the null is wrong and we're going to reject the null. Probably what we do is we hit a big red button and we shut down production, and we want to verify that there isn't necessarily something wrong. Okay, it could be a type 1 error. Maybe we just got some light samples or something, or light bags in our sample. But it could be something more serious. Maybe there's a machine that's not dropping out enough pretzels. I don't know how pretzels are bagged. But really, that's what we're after. We want to. It's kind of it's a quality control check, right? Okay. So let's go ahead and crunch some values for this. So we've identified this is step 3. We've identified the Z statistic as the test statistic that we're after. In step 4, we're going to formulate the decision rule. And here we're smushing together step 1, 2, and 3. Okay, so step 1, we know the null and alternative. We know that it's a two-sided test, right? That's really what we can take away from step 1 is that it's two-sided, right? We're worried in both directions. In step 2, we know that I'm in the wrong place for this. We know that we are in, we want a 10% level of significance. And then in step 3, we're dealing with the Z-score. So we're smushing all of that together, and we're basically saying what Z-score would we need to hit the big red button and reject the null hypothesis that everything's fine. So let's calculate that or let's put a number to that Z-score. So we know that you can look this up yourself, but we probably are getting familiar with those the Z-scores for these values. So remember, this is we're talking about a 10% significance, but that is the flip side of the 90% confidence interval, right? Confidence intervals on the inside of these values. The level of significance is on the outside. So in both cases, we're talking about the same cutoff point, right? Or what we call critical values. Okay, so this dividing line here, those are what we call the critical values. And that is going to be the familiar 1.645 for this case. Okay, in the 5%, it's the 1.96. And so, as you do more of those types of numbers kind of percolate in your head, and you don't even need to turn to the Z table. So we know now that if we take a sample and we calculate the Z-score and it's beyond 1.645, we're going to then reject the null hypothesis. Okay, we're kind of doing, in some sense, in step 4, we're doing the end of our normal process before we even take the sample, right? And so in chapter 9, we often took a sample, calculated it out, then went to the Z table. Here, we're basically going to the Z table first and setting up the process, trying to speed up the process in step 5. So this is, you could think of it as plus or minus. If we're beyond 1.645 on the Z-score, we'll flag it, we'll hit the big red button, and we'll evaluate some more. Okay, so let's say we've run a sample, and let's pick a value that we got. Let's see. So let's say we got a value of 282. I think we talked about that earlier. So we got a sample of 282 out of these 15 bags. This is a value where we really should crunch this, because I don't know off the top of my head if that's far enough away. Right? If we got 289, we'd probably be pretty sure that that's close enough to continue production. So we get a sample mean of 282, and let's go ahead and build that or calculate that Z-score. Yeah, we don't need our rectangle bags of pretzels up there. Okay, so we got X bar of 282. So our Z that we're going to calculate here is 282. Whoops. 282 minus 290. Okay, so we're a little below our hypothesized mean, so we're going to have a negative Z-score. but is it going to be beyond 1.645? We're in the Z statistics, so we're going to plug in our population standard deviation. Again, we're pulling that from previous processes and we did a sample of 15, and so I don't know what the square root of 15 is. 3 point something, 3.8, 3.87. So 5 divided by the square root of 15 is about 1.29. Okay, so what have we found? We have, this is -8 divided by 1.29. And so right away, that's we can finish this out, but that's going to be a very large Z statistic. Oops. And so let me just plug that in. We get a negative Z of 6.19, roughly. It's actually 6.2. We can round. Either way, that's in a very extreme result, right? So that's very far on the outside of the distribution. And so we would want to hit the big red button and dig into what's happening. Maybe there's something broken in the machine. Maybe somebody's eating pretzels along the assembly line. But we need to look deeper into this. And so that's really the process. We've found the Z-score beyond our critical value. Another way we refer to this is that it was in the rejection region. Okay, we didn't write that down here yet, but the shaded regions here are what we refer to as the rejection regions. Just gonna abbreviate that. If we find a Z value that far away, we reject the null hypothesis. And so really what we are saying is that we have enough evidence to say, let's reject the null hypothesis and go with the alternative that the mean weight in these bags is not 290 grams. If I can get out of the way of the alternative. Yeah, and so we would shut down production, go in and take a look. Okay, so that's the general flow of what we are trying to do and what we do here. A couple points to then clarify. Now, it could be true that the null is still correct, right? We are rejecting. We are saying we have enough evidence, to reject it, but we never prove anything definitively, right? So statistics can never tell us anything is 100% true or absolutely prove anything. All we can do is present the evidence and determine if that is sufficient evidence to either reject or not reject. So it could be true that we have made an error, right, and the other day, if you were on, we looked at, right, the type 1 and type 2 errors. Oops. Just gonna pull up let's see, it's in here somewhere. Here we go. A little more structured. And yeah, so there is a chance that we have made an error. Okay, and that's something we always want to keep in mind, that we could have created or made an error. In this case, the only error that we could have made is a type 1 because we rejected the null. Okay, so we rejected the null hypothesis, but it is possible that the null is in fact true. And jump up here. Okay, so really what we're saying is that we know that we've rejected the null. Okay, but we don't know for certain that the null is true. All we can say is that the null is false. Right? We don't know that this is necessarily 100% true. We're just saying that we can statistically reject the null hypothesis, and so we can work with the assumption that the null is false, and we'll work with the alternative hypothesis. But of course, we could be making a type 1 error. I'm not very good at circling those. And just to drive that home, that means that yes, the bags do average 290. We just happen to find a sample that was on the low end, right? And we know that that's possible. We know that when the sample, or when the population mean is 290, it is possible that we find a value way out here. And in fact, we found one that is quite extreme, right? We found a z of -6 something, which is quite extreme. Now, it is still theoretically possible, and so we could have made a type 1 error, right? And that's the in the pregnancy example, that's the man here being told that he's pregnant, and the false positive. So that's always a risk. And so in our case here, so this is where I said, oftentimes when we're determining the level of significance, we want to have this in mind. In some sense, what are the costs of making these types of errors? So for us here, type 1 error, we've shut down the production. What has that done? It's probably slowed down our production numbers, right? We're going to produce less today because we had to shut down for however long. Maybe it takes us only 10 minutes to verify everything. And so we'll need to kind of weigh that. So what is the issue if we make a type 1 error? It costs us a little bit of money. Okay. Now on the flip side, we're going to weigh that against type 2 error, and if we're missing not shutting down when we're supposed to. Okay, so these are the decisions where or these are the things that we want to weigh when we make that decision for alpha. Yeah. So alpha is really how likely it is that we make a type 1 error. Okay, so when we increase, so because we're at 10% alpha, we have a 10% chance of making a type 1 error when the null is in fact true. Okay. So I think it'll be helpful. Let's run through the process another time. Let's do another example. But again, if people have questions, please feel free to stop me. But we're going to run through a slightly different example. I'm going to get rid of some of these. What else do we want to lose? We kind of want to keep that. Whoop, I'll come back. Okay, so let's do this process again. Perhaps it'll go a little quicker. And now I have lost that. I said I was going to keep that. There we go. All right, so another kind of situation that might arise again is let's work through this example. So let's say the state of Minnesota is concerned about the rapidly increasing squirrel population, and they are willing to or maybe just the Twin Cities. The Twin Cities are concerned about how many squirrels we have, and they've told Hamline campus that they'll pay to come in and relocate. Maybe they will relocate them. They'll locate them to a farm up north. If there seems to be too many squirrels on campus. And they've set the limit at if there are at least 35 squirrels on campus, or an average of 35 squirrels, they'll pay to come in and remove them. I might be wildly undershooting. There's probably many more, but let's go with the statement of 35 squirrels. Now, they've said if there are at least 35 squirrels on average, then they'll pay the money. If not, they're not going to do it. So let's set up that null hypothesis. So here, really what the state wants is, the state may come to Hamlin and say, you need to prove to us that there are 35 or more. Okay, we're not going to just give you the money willy-nilly. And so they're going to say, we're going to assume that there are not. So let's assume that the mean is less than 35. Actually, let's make it the math a little simpler. They say there needs to be more than 35 squirrels. Okay, so if there's only 35 squirrels on average, they're not going to pay for this. The alternative here, I could draw an A, is that the mean is in fact greater than 35, and so the state or the city will pay for the relocation of these squirrels. Now, how do we prove that? Well, the state wants a little more evidence than just a picture with more than 35 squirrels, and so they require you to take a sample every day for 7 days, or to take a sample including a picture of 7 days. And so we do that, and we find the following squirrels. Okay, so we find 27, assuming we have some nice spy camera. We find the following number of squirrels. I'm just kind of making this up. Actually, let me fudge that a little bit. Okay, so we find the following number of squirrels every day. This is, I think I want this to be a 7 just for ease. Now, have we proved to the state that there are in fact an average of more than 35 squirrels a day, or at any time? Well, let's see if we have enough evidence. And the state has also said they need a 5% level of significance. Okay, they want to be pretty sure. We need to produce enough evidence, a little higher evidence than our shut down the production facility. So we have an alpha of 0.05. Okay, so we know step 1 and step 2. I guess we kind of jumped ahead. We didn't need this sample yet. So let's I've gone out of order. So I've done poor. I've done poor statistical. We'll just copy that over there so I don't have to redraw it. So yeah, so we've done step 1 and step 2. What test statistic are we going to use? Well, what do we have? We probably don't know the population standard deviation, right? So it's unlikely that we know the population standard deviation of the number of squirrels on campus. And so we are left using the t statistic. Okay, and that we're going to rely upon the sample standard deviation. And so we'll use that t distribution. And so we're going to, step 3, we've established we're going to use the t statistic. where we insert S instead of sigma. And of course, then we're working with those t distributions depending on the sample size, and so yeah. So in step 4, we're going to formulate a decision rule. Let's pull up, if I can find it. We're going to pull up, not that. We're going to pull up the, let's just display capture it. There we go. So we can pull up the T table. Okay, we can zoom in here a little bit if we some of this. And we now need to find, let me come back on the screen. We need to find what T value when we run our sample, which I accidentally already did, but when we run our sample, what T value is going to reject the null hypothesis. Okay, so a couple things. We need to remember that we are dealing with a one-sided test, right? So the state has said the state has said it needs to be greater than 35, right? So we're working under the assumption that there's less than or equal to 35. We need to produce enough evidence that it's greater than 35. And so this is a one-sided test. We need to show, or if we don't have enough evidence, we have to stay with the null hypothesis. We're trying to see if, in fact, we fall on this high end. Okay, and so if we find a sample that says there's 19 squirrels, that's obviously not going to reject the null because that's included in the null hypothesis. Okay, so a one-sided test. So let's go back to our T table. A one-sided test means that we are in the one-tailed test. Okay, and we said a 5% significance level. And so we are working in this column. Now, that again is going to be in the column that is the 90% confidence interval. So it's not, in this case, the 5% is not the flip side of the 95% confidence interval because we're only talking about one side. And again, this should make some sense because, again, if we're talking about 5%, well, yeah, there we go. If we're talking about 5%, then the 90% confidence interval would also include another 5% over here. And that's why the one-sided test is the same column as the 90% confidence interval. That cutoff value, that critical value, is going to be the same. We're just only going to associate with the high end. So what do we have? We have a sample size of 7. Right, so we're going to take maybe we're taking a picture every day at noon. I don't know if that's when squirrels are most active. And so we come on down to our degrees of freedom. Now our degrees of freedom is n-1. So we're going to actually use 6 here. And so the T value that we're going to be concerned about is 1.943. 1.943. Let's get rid of that. So 1.943. There we go. And so that is the T value that we are going to call the critical value. And it's only going to be true for positive. Okay, again, I keep reiterating myself there, but if we find a T value of negative 2.4 or negative 6.2 or whatever we found in the previous example, that's not going to be enough evidence. In fact, it's no evidence that the mean is above 35. Okay, so we found our T value. Now we can turn to that sample that I am now pretending that we haven't already gotten. Although this does highlight that oftentimes, in this case, we could do this all before we take the sample. A lot of times we already have data that we're working with. So maybe we're researching something and looking at data from 1970, and so the data already exists. And so a lot of times the process is we should make sure that we're not looking at the data until we've set this all up. Okay, and that gets into some kind of shady ethical areas, and we can talk more about that probably next week. But the concept of we'll discuss kind of p hacking and some of those concepts as to how it's sometimes if we're in our data before we've set up our process, it can be problematic. So we have set up our decision rule. We can now look at do I still have it over here? I lost it. Where did it go? Okay. So we took a sample. I can write this down again. Of 27, 31, 42, 39, 41, 42, and 37. And so we now can calculate a sample mean. You can double check this, but I think the sample mean is 37. So this is obviously above what our the 35 that we're interested in, but is it enough? Remember, of course, that we are taking a random sample. And so, again, this is the distribution of X bars. So even if the mean of 35, it doesn't mean that just getting a sample mean of 37 is enough evidence, right? That's going to happen occasionally. Now, is this beyond our critical value? Well, we need to transfer it to the t statistic. So let's go ahead and crunch that t statistic. Remembering, what did we say? I need to remind myself, 1.943. 1.943 is our critical value. And our t statistic is x bar minus mu over s and the square root of n. So let's plug this in. We found a sample mean of 37. We're assuming the mean is 35. Okay, so if the mean was 35, how likely are we to find a sample mean of 37? Well, that would happen a certain percent of time, and that's what we're calculating here with the t statistic. S, now we need to crunch the sample standard deviation, and I've enlisted Excel to help me do that. And it's about 5.86. And we have the square root of 7. So again, I'm going to let Excel help me out a bit. So the bottom becomes a little over 2. So this becomes 2 over 2.21. And so as you do these, you can kind of become, you can kind of guess what the answer is going to be, and if we're going to have significance or not. So here we have, what would that be? So 2 divided by bottom, we get a t value of positive 0.903. And so how do we interpret this? So in step 6, we want to interpret this, and what we can say is, that we do not have enough evidence to reject the null. We have not proved that the null is true. Okay, so again, it's important to remember that we, in statistics here, can never fully prove anything. What we can say is that we don't have enough evidence to reject the null. And so in this case, the state isn't going to pay for our relocation of the squirrels. Of course, we could be having a type 2 error. Okay, so it could be the case. Now, in this scenario, we have not, let me switch this up. We have not rejected the null. So we are, that's not what I want. So we haven't rejected the null. Sorry for all the mixing of things here. Just go over here. So we have not rejected the null. It's pretty close. And so that might be true. It might be in fact true that the mean is 35. Okay, so it could be true. But it also might be the case that the mean was greater than 35. Right? Maybe the mean is 42. We just happen to get a value that is below our critical value. And that's a concern that we will always have. Now, it is harder to kind of keep track of type 2 errors and the risk for that, but we can crunch that. And so there towards the end of chapter 10, we do have a little section that we learn how to calculate that risk there. And we won't have time today to go into that, but there will be a video posted about that and how we deal with. Oh, that's freezing up. So, but we do have to bear in mind that that is just fully dropping. Okay, so we do have to worry about type 2 error. Okay, so trying to think if there's anything else we should touch on before we kind of head out. But hopefully this gives you a little insight. Now there is also a section we are introduced to what we call the p-value, and the p-value is directly related to what we've just done. And we don't use the p-value as often in these types of situations, but we do heavily use the p-value later on in a few chapters when we touch on regression. The p-value is often how we report our results, and it can be produced here. So this will be our first introduction to p-value, but so in the shorthand, to kind of get our frame of reference around p-value, largely it's just another way to talk about what we've been dealing with. The confidence interval, the level of significance, and the p-value are all intimately connected. And so the one way to express it is, so we've talked about an alpha of 5%. And we would reject if we found something more extreme than that. And really what the p-value tells us is how extreme something was. Okay, so let's see, we found the t was -6 point something. So that's going to be a very small p-value. So that's not a great example. But if we found a value that was in our rejection region, we might find a p-value of 0.04 or 0.032 or something. So the p-value is just more specifically where in the distribution did you find. In some sense, you can think of it as the percentile calculation, right? So jumping back a few chapters, what percentile are you along this distribution? That's really what the p-value is showing you. Again, assuming that the null is true, how rare is it that you'd find this is really what the p-value is showing. So again, it's in our scenario here, if we have an alpha of 5% and we reject, then we know that the p-value would be less than 5%. So those are just some ways to think about it. Again, we don't have full time here to jump all the way into it, but there will be videos on it, and you can read up in the book. But hopefully that kind of gives you a sense as to what it is. And if it doesn't seem to be incredibly useful in this chapter, that makes sense. Okay, so we don't actually need it to do what we've been doing, but it will be very helpful in future chapters. So it's a good time to be introduced to it. And lastly, what I'll say on that is that the p-value is useful, and it's a good way to organize our thoughts. Now, it is sometimes a little overvalued, and there's kind of a broader discussion happening in statistics or concern about the influence of the p-value in practice. And so we will probably not in this chapter, but when we get to regression, we'll probably talk a little bit about those concerns and try to address those. So, but we will stop there. So hopefully this gives you a little more practice with this. And again, I will be on office hours at 1:30 to 2:30. If I'm, again, just to reiterate, if I'm not there or if I'm not in the virtual room, probably just means that it's not pulled up. But I will get an email. So hang out there for a couple minutes, and I should jump on if I'm not already there. And I'll stick on here for a minute if people have questions right now.